In this segment, I'll be talking about how to use matrices in RStudio. So as I explained in the first segment, in order to get a new syntax file, you're going to go to the green button and you're going to press RScript. You can also go to File, New File, RScript, but it's a lot easier to just use the icon. If you want to open an already existing file, so if I click out of first exercises and I want to open it up exercise, I can go to open file, and then I'd want to go to where that file is at and open up first exercises, and it would be there. Okay. So where are all these exercises? The exercises are in DePaul D2L. For the matrices, they're going to be under the week 1 matrices folder under content. So if I go to content, week 1, they're going to be in the week 1 folder under our examples. And so if I go to the arrow and go to download, it will download to, usually the generic folder to download is to the download folder, and then you can copy and move it to what other folder that you want to save it in. Extract out of the zip folder, and then so if we go through that process, download, click on the folder, then hit go to downloads, and then go right click to extract all, go through the process, and then it'll extract all the files for you. Okay. So in RStudio, the first exercises that we're going to cover are the matrices. So the first thing that you need to know is that a hashtag can be used for writing comments. So if I wanted to say this file uses matrix operations, I can write that as a comment. It's not going to think that I have to access code for it, or syntax. And so then in that case, it will just be read in as a comment and not be given an error that it's a something that has a function or formula in it. If I don't use this hashtag, then it will give you an error like R doesn't understand because it's not a known function. Okay. So those are comments. The other thing that we need to know about is the difference between matrices and vectors. So remember we were talking in class that vectors are one-dimensional. They're either one row, one column. They're not more than one column, they're not more than one row, and they don't have, well, I should say they're just one row or one column. So then the next thing is to understand how to read in a matrix. So if I want to read in the matrix 1, 2, 3, and I want to read it in a certain way where I have 3 rows and 1 column, then I'm going to read in this line, and if I do Control Enter, I can read it right away instead of having to use the run function up here, but I can do that too. And we'll see here that as soon as we create this vector, and I should also note here that I set this matrix to a letter. And so by saying V equals, I set that to be that V should equal this particular matrix, and that matrix includes 1 through 3 by 1, and the numbers are 1, 2, 3, and it's a number type of matrix. That's the data type, I should say. And then if I want to read what that matrix actually is and how it looks, then I'm going to type in V and execute that. So if I execute V, then it's going to show me a matrix with 3 rows and 1 column. So this would be a column vector. In a second, I'll show you how to transpose that vector. Actually, let me do it now so you can see how it works. So if I transpose V using TV, it's going to transpose this column vector of 3 times 1 dimension into a row vector of 1 times 3. Okay. Now, if I want to create another vector, I'll do the same thing. So I'm going to create a new vector with 4, 5, 6, where it's going to be 3 rows and 1 column. So a column vector of 4, 5, and 6. Now, if I want to create a product of 2 vectors, what am I going to get? I'm going to get a scalar number, one number, not a matrix. So how do I do that? In this case, I have 2 column vectors. Can I do multiplication of a scalar, multiplication of vectors to get a scalar if I have 2 column vectors or 2 row vectors? And the answer is no. In order to do multiplication of vectors, I need 1 column vector and 1 row vector. So because I have 2 column vectors, I need to transpose the first one into a row into a row vector from a column vector so that I can do the math. So this column vector, when it was transposed, gave me a row vector, and its dimensions 1 times 3, and the W dimension is 3 times 1. Because this 3 is the middle 3 here as well, then I can do that math and get a 1 by 1 scalar answer, which is our product of the 2 vectors. So let's see how that works. So I'm going to set this formula of T transpose V, the first vector, times the second vector. Notice that in order to do multiplication of vectors, I need to use percents on each side of the multiplication. So put parentheses on each side of the multiplication to do the products of 2 vectors. And when I do that, I get my scalar answer of 32. How did I get that answer? Remember from class, this is when I take 1 times 4 plus 2 times 5 plus 3 times 6 and sum them all together, and I get the scalar number. Now see what happens if I do this, but I don't have the percents in there. So let me multiply. So I'm putting it in the console because I don't want to have the wrong answer in my syntax, but I want to show you what the wrong answer will look like. So if I don't use the percents and I do the multiplication, it's going to say non-conformable arrays. It's giving me the scalar answer because I already had the scalar saved here. Okay, but if I do the without the percent signs on each side of, it's going to give me an error, and it's going to say, I don't understand what you want me to do here. So in order to get the answer right, you need the percents on each side of the multiplication, and so when you run it, it will give you the right answer of 32. Okay. For when you have 2 matrices where one matrix is 1, 2, 3, not matrices, vector is 1, 2, 3, and the other vector is 4, 5, 6. Okay. All right, so that's using the dot product to come up with a scalar number when you multiply 2 vectors together. From here on out, we're going to be actually using matrices where we have more than 1 row and more than 1 column. So how does this work? So let's say, for example, we want to add 2 matrices together. I'm going to say 1, 4, 3, 2. It means that I'm reading it in, when I say by row equals true, it means I'm reading it in row by row. So the first row had 1, 4, and the second row had 3, 2. And then I say, what is the size of this matrix going to be? I want it to be a 2 by 2 because I need 2 rows with 2 columns of data in it. And so when I read in these 2, yet again setting this sort of function slash formula in to create the matrix, and then call the value or the letter that I set for that matrix, I will get this answer. So what it means is when I wrote in here 1432 is that on the paper, just like in your homework assignment, it would read something like what the numbers were in this first row and what the numbers were in the second row. And so if you're comparing this to like a homework assignment, you would make sure that the way that it looks here is the way that it looks like on the page of your homework assignment. Mind you, the values are different here than in your homework assignment. This is just an example. And if we look at this, we'll see that the dimensions are 2 rows and 2 columns. Remember, rows are horizontal and columns are vertical. If I wanted to read it in by columns, then I would change the by row to equal false, that I'm not using rows, I'm using columns. And then I would read in the data 1, 3, 4, 2. Okay. And so that would look like, if I change that here, Control C to copy, Control V to paste, and I can put in 1, 3, 4, 2, and say that by row is equal false. And I'm going to reset this to a new thing so we don't compromise the other. And if I enter that, now it's showing the same thing, but it's showing me that I was reading it in by columns instead of reading it in by rows. Okay, so you can get the same answer, but you're reading it in 2 different ways. One by rows, and then one by columns by row equal to false. Okay. So then we would do the same thing for the second. And then in order to add, I'm going to add both matrices by saying M, the first matrix, plus N, the second matrix, will give me my answer, which the answer of addition is a sum, and then call that sum, and I'll get my answer. So if I add these 2 matrices together, I'll get this answer. And how does that work? 1 plus 5 is 6, 4 plus 3 is 7, 3 plus 1 is 4, 2 plus 7 is 9. Okay. Then I can also create 2 new matrices. Now I'm overriding the previous matrices because I'm setting it to new things and calling up the difference. The difference is the answer of 2 things when you're subtracting them. So in this case, when I create the new matrices, subtract them, I'll get this difference. And so how do we do that? 2 minus 3 is a negative 1, and so on and so forth. Then if I want to multiply by a scalar, I'm going to create the matrix. And in this case, I'm creating one vector. And I'm saying I want that vector to be 2, 4, 6, and have it be 3 by 1. And then multiply that vector by 5. So if I create the vector, I get 2, 4, 6 as a column vector, and then I multiply it by the scalar of 5, and I get 10, 20, 30, because 5 times 2 is 10, 5 times 4 is 20, 5 times 6 is 30. Now remember, if I multiply by a number greater than 1, the numbers are going to get larger. If I create a new matrix, a new vector, and I multiply it by a scalar of 1/3, something that's less than 1, then the numbers are going to be smaller. because 1 times 1/3 is 0.333. 2 times 1/3 is 2/3, which is 0.67. And 1/3 times 3, 3 times 1 is 3. 3 divided by 3 is 1. And so the final answer here is just 1. Okay, and then if we want to multiply matrices, we want to first create the matrix, and then we want to check what the dimensions are. Remember, dimensions are row, column. So this is row of 2, column of 2. Create a second matrix, check its dimensions. Is this number the same as this number? Yes. So I can multiply these two matrices together without having to do anything else. If it wasn't, you could potentially try to transpose, but that might not make sense for the application, the field of which you're doing the problem in. For the homework assignment, do not transpose if it's not the same, if the dimensions are not allowing you to multiply it, then just say you can't multiply it due to different dimensions. Yet again here, in order to multiply two matrices, just like two vectors, you need to use percents before and after the multiplication sign. So if we create the product and then call up the product, we will get the answer. How do we get this again? 2 times 1, that's not the correct answer, because when you're doing multiplication, you have to multiply by the row and the column. So so you would do the multiplication of the row times the column of each cell and get that to be each of these individually. In terms of transposing, we saw that already. You would transpose, create the vector and then transpose it. You can also transpose a matrix. So if we transpose the matrix, then we would get something that looks like this. So what ends up happening is this column vector of 4, 2, 8 now becomes, or I should say the column in the matrix 4, 2, 8 then becomes a row 4, 2, 8. And the same with column 2 becomes now row 2. Okay. And then from our slides on matrices, we saw that there's a theorem that says if I take the product and transpose it, it's the same thing as if I originally transposed M times originally transposing N. So how does this work? So we create M and N matrices. We take the product of M and N, making sure to have the percents before and after the multiplication. So that's the product. And then we transpose that product. And so the answer to the left that theorem of M times N transposed is 5813. Now, if you wanted to prove that it's the same thing as transposing N times the transpose of M, we would do T to the N times T to the M. So it's gonna transpose these first and then multiply them together. And so if you do that, you'll come up with the same answer. Now, Library Pragma is not part of the base package or the stats package. So this would be a package that you'd want to install. So you first go to install packages, or if you want to do the shortcut, hit the icon here, and you would type in Pragma, hit install. and would go through the process of installing it. And then in order to execute this function, which is RREF, you would have to call up the library so it knows where to find that function. I don't have to install the package Pragma again in R, because when I open the next session, the package is already going to be installed in my location for the packages. But in order to use the function again next time, if I reopen this syntax, then I would have to call up the library. Normally the library should be at the very top, but because we're using this and I wanted to make sure you understood when you would use this, I put it further down in the syntax file. So in this case, we've called up the library, we create our matrix, and let's say that we wanted to solve, this is going back to sort of the example of when we want to solve for our slopes, which we'll get to in the next exercise with the first exercise. Then we're going to create the matrix and set our dimensions, how many rows and columns, and then say that we're reading in by rows. And we create it and it looks like this. And then if we want to solve for beta naught, the intercept, and beta 1, the slope, we want to make sure to get all of this 1, 1, 2, negative 3 to look like an identity matrix where you have all ones down the diagonal and then zeros on these diagonal. And then solving for here what the actual beta naught and beta 1 are. So if you want to do the shorthand and you just want the final answer, you don't want to see the work of how that goes about, remember this is from our linear algebra days, then you can just use the function RREF of that matrix, and it will do Gaussian elimination for you. So it gets us that identity matrix on the left side, and then the answers that we want on the right side. So if this was solving a system of linear equations, solving two equations to get the beta naught, the intercept, and the beta 1, 3 here would be the intercept of beta naught, which is beta subscript 0, and beta 1, which is beta subscript 1, would have the slope of negative 1. And then if you wanted to write that out as an equation, you would write that out as y hat, which I can't really do here, equals 3 plus negative 1 times x. If I hit enter here, it's going to tell me x isn't found because I haven't set x x to nothing. So if I say that x equals 2, and then I re-put in this function, it will then say I've saved the formula, but then in order to know what y is, I have to type in y, and it'll tell me it's 1. And why is it 1? Because negative 1 times 2 is negative 2, and 3 plus negative 2 is 1. Okay. If you wanted to be on the safe side, what I would usually do, because order of operations can sometimes get tricky if you have multiplication and division, and you for sure want this to be done first, you would want to be on the safe side and put parentheses here. In this case, it doesn't matter, but sometimes it will matter, particularly if it's like x plus 2, and you need that to be done first before like some multiplication. Then just remember your grouping symbols are always important for making sure what needs to be done first, and then next, and then after that. If you need to show your work, so let's, if it was back in the days when we actually were taking linear algebra, we can use the library matlib. So you would go to install here and type in matlib to install that package. So we'd install it here. We'd call it up so we could execute it. So what I've done here is I've done manually to try to get down to our final answer from using it the shorthand way for Gaussian elimination. So in this case, taking the original matrix M, which to recall M was this matrix, I could then do the diagonal so I could get it set up to do Gaussian elimination. And then I could use row operations. So remember, I can add 2 rows. And so in this case, it would be saying adding 2 rows and then subtracting them. And then I can do row multiplication where I want to multiply row 2 by 2. And so if I do that, we get this answer. So we're getting a little bit closer to getting the identity matrix on the left side. I can do an additional row multiplication by multiplying the first row by 5. Okay. So that's close to me getting this closer to 0. And then I can say, well, I want to add these 2 rows together. So if I add these 2 rows together, then I get this 0 here. Because I added row 2 to the first row to get 0 here. So now I'm getting closer. I have the zeros on this side, but then I now need to get the 1s on this side. So here I can then multiply the first row by 1/5, and that gets rid of the 5. And then I can multiply the second row by -1/10, and it'll give me +1 on the bottom there, which then leaves me with the answer of the beta knots, and then also provides me the inverse as well. Okay. And then if I wanted to show the long way instead of having to do the long way manually, then I can use echelon form, and it will give me the shorthand answer of what I just did. And if I want to show my work, then I can say use the same echelon, but say verbose equals to true, and use fractions equal to true. And if I do that, then it will look like fractions. If I didn't want to use fractions, I wanted to use decimals, then I can say equals false. And so it'll give me decimals like I had instead of fractions. Okay. And it'll show me all the different steps that it took. Now, the steps from the echelon method are not the same as the steps that I used manually here, because I wanted to show you that you can solve it different ways and still come up with the same answer. Now, the way I did it wasn't as computationally shorter. There's fewer steps when based on the way that they did it in the echelon form, but most of the time you might not see right away what you necessarily need to do, and so it might take you some more steps, but you eventually can get down to, as long as you're doing the right, you're following the rules of row add and row multiply, you can come up with the final answer in the end. You do not need to use the Gaussian elimination for the homework assignment, but it is there in case you would need it, later in your studies, or using matrices in like econometrics or some type of other analysis. You know how to do it in R now. And remember, matrices are the foundation to linear regression, all the other methods that we're going to be using going forth in this class. So in that case, you don't, it's important for you to understand how they are and what they're doing in the background. But from here on out, you're not going to have to do the manual matrices to get your answers, but have some comprehension of how that's being done in the background. Particularly if your answer ends up coming with a bug or an error, and you sort of need to know how that came about, understanding of what's sort of being done in the back end helps with that. So now let's look at the first exercise. This was showing how to do linear regressions manually using matrices. And then next week in class, I'll show you how to use the problem 5, how to use examples relating to the problem 5, homework 1 problem 5, using the actual LM function with reading in data. Okay. So when we're doing the manual reading in of the LM function, okay, what you need to know is that because we're reading in this data manually, we're not reading in a data set, we need to make sure that we put in ones for as many rows as we have data, because the 1 is going to create a constant, that beta naught, and so we need that in order to do it for each row, so eventually we can get 1 constant for the formula. When you do the LM function, as we'll see later on, you will not need to use that because in the background it's already doing it for you. Okay? But when we're doing it manually using the matrices to sort of show how the matrices are being done in the back end of LM, you need to put in those ones. So I'm going to create the Z matrix. The Z matrix is going to include our constant ones, our X data, so that will include X1 and X2 data all in a row. We're going to say we have 8 rows and 3 columns because we have a constant. We have X1 and we have X2. So what that means is column 1 is going to be beta naught. Column 2 is going to be the beta 1 for X1. And the third column is going to be beta 2 for X2. So we're going to create the Z matrix, and as you can see here, constants X1 and X2. Remember, when we're taking data from a table to a matrix, we're not going to see the labels. We're taking those off, and it's just a matrix of numbers. Okay. And then and particularly here, because we're creating it with a matrix, there are no labels for the columns as well because it's a matrix. And then we create a Y matrix for the Y values. So in row 1, we have a yield of 5,755. Okay. Remember, this is from the example in class where X1 is plant height and X2 is tiller number. And the Y matrix is the yield for the grain. So when we create the Y matrix, we get a Y matrix that is a row with all the 8 different yields for the 8 different rows. Okay. Next is the formula for how to solve for the beta. So beta equals, now this is a very long formula where a lot of different things are happening at the same time. So what are we doing here? First, we have this bit going on, and there's actually 3 things happening here. We first are transposing Z and then multiplying it by the original Z, which will give us a product. And then that product, we take the inverse of that product using solve. Remember, in R, it does not use caret -1. You have to use the solve function or G inverse. And so in this case, solve is under the base package, so that's easy to do. So once we've transposed Z and have that answer, multiply it by the original Z, we get that product, and then we take the inverse of that product using solve. And then it sort of temporarily saves it away. And then in a second area, we're transposing Z and timesing it by that first answer after we've said and done all the three different parts of it. And so then that's sort of saved, and then it multiplies that answer by y. Okay. And remember, all of these dimensions have to be making sense in order for multiplication to work. And so in that case, it does. And when we solve this, set this formula and then call it, we get our answer for the betas. So this is the same function that we see in the slides for when we're talking about the matrices with grain yield, plant height, and tiller number. So the intercept is the 6,335 decimals. Beta 1 is for plant height, -23.75. And then for the tiller number, we have 150.31. Now, sometimes you can get a lot of decimals, and sometimes you only just want 2. So out of the base package, library stats, because it's under the base package, you don't have to keep calling up library stats. You can use the round function beta. So take this answer, round it to 2 decimal places, and call it something else. The reason why I don't call it the same thing is that in case something, there's a bug in the issue, or I set the wrong number of decimals, it doesn't rewrite what I already did. So in this case, I create it, and so now you can see that instead of having 4 decimals, I have 2 decimals. So that is how to do linear matrix, or how to do linear regression manually using matrices. Now we're going to take the same information, but we're going to use it as we're going to use the LM function under library stats. Yet again, it's under the base package, so you don't have to keep calling up library stats. You can just call up the function. So in this case, when we're doing it using the linear regression model function, we don't need the ones here, because in the LM function, it's going to already put in those ones. So I'm going to call the Z matrix something new, because I don't want to override those ones from the manual. And so I'll call it Z2. And if I show you what Z2 is, we're going to get just the X1 and X2, because it's going to, in the formula or the function for LM, it already sets up a line of code to put a column of 1s. And then what we're going to do is we're going to call the linear function ln.mod. You can call it whatever you want. The reason why I did it this way is ln stands for line, mod could stand for model. And in this case, because I'm setting a model function, I need to use the caret arrow. Okay, so some things you can use equal signs, and other things you have to use carets. And this is not defined, so how you would do this is you would write ln.mod, and you would use the caret sign, which is shift comma, and then you would use shift dash, which is, I'm sorry, not shift, just dash, which is next to the 0. And then you would type in lm, which is the function. Y is your dependent variable. And the way that they wrote out the lm function, you use tilde, which is shift, and it's that button next to the 1, to the left of the 1. If you use shift and that button, it'll give you the tilde sign. And that's sort of like the equal sign for the LM function. And then you would put in your matrix that contain your X variables, your independent variables. So yet again, this is Y variable, which is your Y matrix, and then the Z matrix, or the matrix that contains all your X variables that do not include Y. So when you are creating, when you need to run a regression, and obviously this is going to come from this may come from data in all one data set, you're going to have to subset out your Y variable from your matrix of Z variables. And I'm going to show you in the examples with the read HBAT when we cover that regarding problem 5 concepts when we're actually reading in a data set. So in this case, if I read in ln.mod and set that function and call it, I'm going to get this. And simply what it's just giving me is what the line is with the coefficient, intercept, the slope for beta 1, which is the plant height, and then beta 2, which is the Tiller number. And the way it quantifies it, it says this is coming from matrix Z2, where this is the first column, and then this is the second column. Okay. And the matrix was Z2, so that's why we get, it's going to give you the matrix name and then the column number. So column 1, and then this one was column 2. Yes, it helps in writing the line, but it doesn't tell you if the line is significant or not. And the only way we get that is if we use the summary function. So we can determine whether that model is a good fit if we use the summary function. So the first thing that we're going to do, and I sort of hate that it doesn't show it as an ANOVA table as you would see in a standard statistics program like SAS or SPSS or Stata, but the important information that you actually need in here is down here, the F statistic, and it'll give you the degrees of freedom for the model or the regression, which is the first row of the ANOVA. And I'm sorry, this is the F statistic. Degrees of freedom for the model regression is 2, and then the error, which is, or the residual, which is the second row of the ANOVA, is 5. And I believe if you do ANOVA ln mod, actually, yes, ANOVA ln mod, it should give you the ANOVA. And so it'll show you that the model is degrees of freedom 2 with sum of squares model. Then it'll give you the mean square, the F value, and the P value. And it'll give you the residual degrees of freedom, the sum of squares residuals, and its mean square error. Remember, sum of squares divided by degrees of freedom give you mean square, and mean square model divided by mean square residual gives you the F statistic. And then using, well, in the old days you would use tables, but now it will generate a VLOOKUP table to tell you what p-value to use for that test statistic. And then it will tell you if it's statistic at what level. So going back up to here, when you use summary, you want to first look at all you really need to determine the global information is this p-value. And if this p-value is significant, then you can go on to interpret what the independent t-tests mean. So in this case, we see that the F statistic is significant, okay? So that means we can interpret the coefficients, but when we go to interpret the coefficients, we find that the X variables 1 and 2, plant height and tiller number, are not significant, okay? So we may then have to go and figure out why that is. In this case, it's probably because we only have 8 observations, and so there's not really enough data to substantiate an association, and so we might have some type of overfitting going on here. If I try to use VIF of this function, it might tell me some answers. And actually, in order to do the VIF, we'd have to do it in the LM function, and we'll cover that next time in the problem 5, because with this being so small, it wouldn't be very helpful here. Now, the one thing that would be helpful, because we only have 2 variables, is to look at the correlation. And in this case, you have to have all your variables in a matrix or in terms of a data frame all in once to get this to work. So if I do the correlation of Z2, which contains my variables X1 and X2, and let's just say we set that equal to, let's say, R, we can set it and then call it, and it'll give me the correlations between these two variables. And as we can see here, the correlation is 0.77. There's an inverse relationship, but the correlation is above 0.7, so they are highly correlated. And so it probably says we probably should use one of these variables instead of both of these variables. But yet again, if we go down to one variable, it's going to be a very simple model, and it probably won't make application sense. But we can't use both of these variables together because then our model will overfit, and then we'll get these results where the f is significant, but the t-value is not significant. So if we're looking at these coefficients information, the global f-test hypotheses would be, are beta 0, beta 1, and beta 2 the same and essentially equal to 0, or are they different, whereby at least one of these beta is not equal to 0? So based on this, we would see that because the p-value is less than 0.05, we would say that the alternative is true, H1, sometimes in some books it's HA, that at least one beta is not equal to 0. So these betas are different than each other. And we know that to be true because when we solved for it and we got these betas here, they're all different. They're not the same values. When we go to look at the individual beta tests, we're looking at this one variable at a time. And so for beta 1, we'd say, is beta 1 equal to 0, or is this beta 1 not equal to 0 if you're doing a two-tailed test? If you wanted to do a single-tailed test looking at only the left side or only the right side, you would either say beta 1 is less than 0 or beta 1 is greater than 0, or whatever value you would want to set to beta. Traditionally, we just use 0. And so in this case, if we're looking at the beta 1, we'd say, is beta 1 significant? And the answer is no, it is not significant. So in this case, it's saying that HO, the null hypothesis, that beta 1 is equal to 0. But we know that to not be true. We know that it's negative 23.75. So there must be some disconnect here, and it's the multiclinarity, the fact that these variables are highly correlated with each other. If we scroll back down here with the negative 0.77 correlation. Okay. So what do we overall understand from this? We understand that while the overall model is significant, where there is a difference between the betas, none of the individual betas are significant, which leads us to show that there is multiclinarity. Okay. If it was significant and we wanted to come up with a predictive value, then we would create the formula and we'd substitute in for our x1 and x2. So initially, sort of like before, we'd have some type of function where it would be the slope times x1, and remember that we'd want to have parentheses around it for the grouping symbols so that you have order of operations correctly. And then we'd have the second slope times x2 plus the intercept. And in the background, so normally here what we'd end up doing is when we're writing the theoretical equation, we'd write down the epsilon e. Unfortunately, I can't do that in R, so I'm using E here. But you'd write in that we know that there's always going to be some error, right? It's not going to be 100% perfect that the line is going to run through all the dots. There's going to be a difference between whether your actual data is above or below, or your model data is above or below what your actual data was. And so in that case, that's where you get those errors. But when you're doing it in R, it is already going to be calculating those errors, unless you're going to be doing a very highly theoretical model. We won't necessarily write that error in there. So there's a difference between the theoretical model and the applied model. So in this case then, if I substitute in x1 100.5 for the plant height, and then substitute for x2 15.3 for the tiller number, and then set this formula and then call this formula, then I'll get the predictive value of 6248.47. And so if I wanted to, I could then try to round this value by doing this, and calling it. And you notice here that because I already called it or created it and set it to the formula, once I start typing it in, it's going to say, what value are you looking at? And so the temporary variable that I created was pred, and so it's going to, as you type in the letters, it's going to try to figure out what you're trying to do with it. So if I highlight pred and then call it, then I round it to 2 decimal places. Okay. So in this case, I've explained how to read in matrices using matrix operations from the Matrices practices. And then I've also shown how to do linear regressions just using matrices manually, as well as how to use that same data outside of the Z2, where you don't have to have the ones in them for the constant, because the LM function really does that, and then use the LM function out of library stats to run a linear regression. Now, in the next tutorial in class, I'll be running through the examples for linear regression, for how to do it when you're reading in an actual data set, so like an Excel file or an SPS file, and how to use the LM function, so how to read in the data and use the LM function with that type of data. Okay, so this ends this tutorial.